Okay, now we go to Tony Orme, who is kind of speaking in an unusual role here. We all know him and love him as the editor of the Broadcast Bridge, but something that I learned over the summer that was news to me is that Tony's actually a great student of digital systems, and he's actually working on his PhD in pursuit of things that are very heavily related to a lot of the issues we're dealing with ST2110, specifically buffers and how they work and how they actually perform. So I'm expecting a really interesting presentation from him today. So take it away, Tony.
Thank you, Wes. Yes, as Wes says, timing is one of my favorite subjects. I absolutely love timing. And I've just started studying at the University of Surrey, and the title of my research is IP Timing Anomaly Detection Using Deep Learning. So what I'm hoping to do is find some of the deep insight into, or gather some deep insight into networks, and specifically IP networks in 2110, to find out how we can make the whole system a lot more efficient. But this is ongoing research, and hopefully I'll be able to update you as we go through the months and years of my study. So 2110, I think it's incredibly important, because what we've done is abstract away the video, audio, and metadata essence from the underlying hardware. So it's a really important change for 2110 and IP in general. So no longer are we going to be dependent on point-to-point dedicated connections as we have been with SDI and MADI and AES. And no longer will we be constrained by fixed, non-scalable hardware systems. You know, one of the great advantages of IP is that we can build and scale our hardware. This is a typical example of one of the applications you'll see for IP. And I think it explains beautifully why 2110 works so well, because at the beginning here, we have the camera, and we're generating our PTP timestamps. And then those timestamps stay with the video, the metadata, with the video throughout the duration of that stream. So it allows us to do things offline or online, and to be able to move resources to the cloud or private data centers. And so we maintain that timestamp within the context of the stream, which helps us then rebuild the pictures and the sound and the metadata afterwards. Because one thing television absolutely demands is continuity. And as we've all know from our pictures of many, many years of working in television, the input must be continuous and synchronous with the output. And I think it's worth remembering, even in these days of digital television and IP television, is that everything must be synchronous. So the camera is absolutely sampling the picture 50 times, 60 times a second, 59.94 times a second, sampling every time. And the display, the video display, is showing those samples, and they're completely asynchronous. And it's been that way since the 1930s. And it'll probably stay that way for the foreseeable future. But the whole point is we're taking a synchronous system, and we're making it work on an asynchronous system. This is what happens, a typical example with audio, if we have our systems which are non-synchronous. So we have a clock generator at the encoder, a clock generator at the decoder, and if they're not synchronized, and say, for instance, this clock is working slightly faster than this clock, then you're going to get drop samples. And in audio especially, if we drop a sample, we know about it. It sounds awful. We get squeaks and pops. So this is an example of why we must absolutely synchronize everything. So within IP protocols versus broadcast, the broadcasting uses dedicated synchronous point-to-point connections. So our traditional SDI connections and AES and MADI connections were all synchronous. The whole point of having SDI was the clock was embedded into the signal, as well as MADI and AES. Now, when we move to IP, we're using two fundamental systems. We've got UDP, which is our fire and forget protocol, which is what ST2110 uses. And we've got TCP. Now, TCP is incredibly important in the IT world, but it's something which is really dangerous for broadcasters. And I'll come on to that in a little while. But this is a typical example of how the clocking system works within a 2110 system. We have our grandmaster clock, and we have a master and slave. One of the beautiful things I like about PTP is it has inbuilt redundancy within the protocol. So if one clock fails, one master fails, one of the other clocks can pick up the gauntlet and then become master. And then we have to make sure that the time stays synchronized through the switch. So we have to have Ethernet PTP-aware switches. And this is really important that our switch is PTP-aware, because otherwise the delay through the switch isn't taken into consideration within the network, and any slave devices will lose their synchronization. So this, I think, is the most important picture broadcast engineers of the future are going to see. This is a typical distribution curve, statistical distribution curve. And in the SDI days, the width of that distribution curve was very, very narrow. We had very, very sort of narrow distribution, and our tails were very, very close to our center frequency. As we move into IP, this whole curve starts to expand. And you can see where the -3 microseconds are here. Within those tails of the distribution, this is where the real interest of my research is going to be. And this is the bit that is going to cause us the most interest as we build IP systems. So the way I think about IP is that imagine yourself sitting on the back of an IP datagram as it traverses through a network, and consider what happens next as you move from device to device and network to network. And that's just one way I visualize in my own mind of how IP works. So I imagine myself as a sample of video leaving a camera, and then moving from the camera into the Ethernet, and then into the switch, and then from point to point throughout the whole network. And that really helps me sort of visualize what's going on in the IP world, because it's so different from the SDI world. You have to start thinking sort of more side to side instead of front to back or up and down. So as our packet continues its journey, our IP packet that's left the camera continues its journey, we have some interesting anomalies that we have to overcome. There's congestion, there's jitter, there's reordering and bursting. And these are not errors. These are things that happen in IT networks and Ethernet networks. And they are a consequence of how networks work. So here's an example of, we have 4 inputs to a switch, and we've got microphone 1, 2, 3, and 4. These are 4 samples, and this is showing what happens in a bursty type sample. So we've got 4 physical Ethernet inputs, and then we've got our switch, which is switching between the 4 because it's multiplexing them onto one output. And you can see on the input here, with mic 4, it sort of occurs at 4 milliseconds, but on the output it occurs at 6 milliseconds, because we've had to move these packets along to make them fit onto the output. And that is one of the challenges we have with IP. If that happens sort of in a burst mode, that's fine, because those packets sort of all find a place, if you like, in the network. But if that happens continuously, then we get overrun, and we can get congestion of the network, and then we'll start losing packets. Another example here is reordering and also jitter. So you can see on the top we've got the sort of the layout of the packet with the IP, UDP, RTP, and then the actual audio sample. The A is for audio in this instance. So we've got an orange, a blue, a green, an orange, and a blue. Then on the bottom, we've got an orange, a green, a blue, an orange, and a blue again. So our green and blue samples have swapped around. And that's a consequence of just how the switch is working. That's it's not in error. There's not a problem occurred as such. There's no issue with that, other than that's what the switch does, because it has to re-multiplex our transmission packets. And you can also see the jitter, where the jitter occurs. So the jitter is the temporal shifting of the packets backwards and forwards within that Ethernet link. Another challenge we have is, if you look at the top picture here, is one of burstiness. So while packets are all beautifully evenly gapped, that sort of works well. But when we get burstiness, we can have some more challenges. So at the top, you can see the very first top diagram, the evenly gapped data. We've got packets 1, 2, and 3 going on a 10 gigabit link. And what I did here was sort of simulated what would happen if you took that 10 gigabit link and connected it to 100 base T. So the data in this example would be 90 megabits a second. So we get our data evenly gapped. And you can see on the second diagram below, we've got 1, 2, 3 on the 100 base T. And that's showing how the packets are temporarily stretched because of the difference in timing between the two links. And that works. So you can see that you can take a 10 gigabit link, connect it to a 100 base T-link, and as long as your packets are evenly gapped, you get a decent output. Now at the bottom, you can see what happens if those packets are bursted. So we've got packets 1, 2, and 3, which are still probably at 900 megabits a second, but because they're happening in a very short temporal time, we have the effect of burstiness. And the diagram below shows what happens if you try and connect that to a 100 base T-link without any buffering. You actually lose the second and third packets. And I think that's really quite important. So here is another example of a non-blocking switch. And what you can see is we have 4 inputs, P1, P2, P3, and P4. And they're creating the sequence on the outputs of the video frames V1, V2, V3, and V4. And this is an example of a non-blocking switch, which must use buffers. Because if you look at P1, we have our inputs V1 and M1 and a V1, and these are individual packets. So V1 is a video packet, M1 is a metadata packet, and V1 is another video packet. And this may happen in a typical scenario if you've got the output of a camera which is creating metadata, because you've got one Ethernet output, and the key to remember with Ethernet is we can multiplex many different types of packets of data on there. So we have some video packets, we have some metadata packets, we have some more video packets. And what this is showing is the M1 is effectively blocking the switch, or would be if we didn't have this non-blocking element, which is the empty and blocked green box below. So the switch is relatively intelligent, because what it will do is look through the buffers and find which packets could potentially block our high-speed video packets, and then move them to another buffer. So the buffer is also a way of letting the switch look through the data and preempt what it thinks might happen, so that we can create non-blocking switches. This is another example of taking 4 cameras, putting them through our Ethernet links on our ports 1, 2, 3, and 4, and then creating a quad split. So you can see that we have red, green, purple, and yellow, so red, green, purple, and yellow on a quad split. And ideally, what we want is each of those packets to be evenly gapped and to time division multiplex within each other. And this is what I believe 2110 wants to achieve, in terms of that the packets are evenly gapped. And if we can then split those into our quad split, so we've got a higher frequency output on our quad split to give us the right packets, then that should all work quite nicely. But the question is this a realistic, can we realistically achieve this? And so the question of buffers is, what problem do buffers solve? And the fundamental answer to that is they synchronize asynchronous events. So the whole point of a buffer in any electrical system, any network system, is to synchronize 2 events. Now remember at the beginning, I said television is a synchronous system. So we have our pictures being generated at 50, 60 frames a second, our monitor displaying at 50, 60 frames a second, and they have to be synchronized. When in IP, when the frames leave the camera, then they go into an asynchronous network. So the PTP helps us know when those packets were originally generated, but it doesn't necessarily help us within the network. It's only at the receiver are we then able to put those packets back together in the right place. So in the middle, you have this whole homogeneous glob of buffers, because that's how IT systems work. They're constantly synchronizing asynchronous events. So if you take, for instance, a website, if you click on a web page, that will send a request to the server will respond with an answer, and those are asynchronous events. And from the IT point of view, they don't really care how quickly they happen within reasonable sort of terms. So if it takes 1 millisecond for the picture to display, it doesn't really matter whether it takes 1.5 milliseconds or 3 milliseconds. It's a rough generalization. But in video, obviously, that's really difficult for us. So when we move to software processing, buffers exist by design. And what I want to try and get over is that buffers aren't there to make our lives difficult. They exist to synchronize asynchronous events. And you get more and more asynchronous events when you process it in software. So if you take an operating system, for instance. An computer operating system is just a load of asynchronous events which are operating serially to give the perception of parallel processing. And when you start receiving and transmitting Ethernet packets within a buffer as well, within a computer as well, it gives the impression that things are happening in parallel, but they're not. They're happening serially. So those buffers have to exist to be able to synchronize all those different events. And what I have here is a example of how a PTP system might work within a software environment. So this is a server. And what I've showed at the top is the server needs to create PTP timestamps. So it will create the PTP timestamp, it'll wrap it within a UDP header, and then also with an IP packet, send it down to the network interface adapter, then into the network. Now, if you look at just the top example, the challenge we have there is that the PTP and then passing on to the UDP and the IP, each one of those revolves around having a buffer because they're handing off different processes within the CPU, within the operating system, which then generates jitter and delay. And so the best way of achieving PTP insertion, if you like, is to actually insert the PTP packet within the physical network interface controller, the Ethernet card. Because you can see on the right-hand side, getting the the PTP packet is just a matter of deconstructing the whole IP packet. So it's important to look where we insert the PTP header as well. So this is then digging deeper into this. So this is the PTP, the UDP, the IP, and into the NIC. And this is what happens when you send a packet within a software device. So this is why doing software in broadcast television is quite an interesting challenge for us. Because we have our application at the top, so maybe this, I don't know, this could be a character generator of some script or a graphics processor. And then within operating systems such as Linux, they use this sockets buffer system to be able to interface the application to the kernel space. And the kernel space is the bit that's the core of the operating system. So to be able to send that data to the operating system, which effectively has to wait, the application has to wait until the operating system is ready for it, the data will be written into a series of buffers. And then from the Ethernet buffer, that data will then be queued, written into a transmit queue, and sent into the driver for that device. And from there, we have even more buffers before it's written into the network interface card. And from there, it goes into even more buffers before it physically gets to the wire. And that's so that the network interface card can make sure there's enough space within the network to be able to send the data anyway. So even in this simple example, we can see there are 3, possibly 4 areas of buffers, of where buffers exist. And again, this is by design. This is not suggesting there's a fault in anything. This is just how software works, because it's trying to synchronize all these different events. So one way of getting around this is using something called kernel bypass. And this is a phrase you'll hear time and time again as we progress through our IP journey and more of our solutions become software-based. And on the left, you can see how within an operating system such as Linux or Unix or those type of operating systems, you have 2 sets of areas of user memory. You have the user memory, which the user would have access to, and then you have the kernel memory in the kernel program. And the idea is you're not allowed to write to the kernel because that will cause all kinds of problems with the operating system, especially with sequencing and with buffering. So the problem there is you can imagine from this diagram of how we transmit just IP packets down into the Ethernet, you've got 1, 2, 3, possibly 4 areas of buffer which are causing latency. And it's not the latency is that much of a problem, it's the fact that it's unpredictable. So not only are you getting latency, you're getting unpredictable latency. And where in this application do you insert your PTP? Because if you insert it at the bottom, where I suggested here, you get reduced clock jitter. However, it's not typical of the timestamp isn't exactly synchronized to the application, because the application has to really insert the timestamp at the top. But if you insert it within the application at the top, as I'm showing here, then you get jitter within your PTP. So it's all a bit of a balance. So one of the areas of interest of research you'll see at the moment, and a few vendors here are achieving, is something called the kernel bypass model. So on the right, you'll see the kernel bypass model. And the key here is you can see the application talks directly to the hardware, which is sort of breaking the rules of how Linux works and Unix and all those type of operating systems work. But it's the only way we can achieve the time and the latency we need to make sort of systems like ST2110 work within software. Now, it's important to realize that the phrase kernel bypass isn't bypassing the entire kernel. It's only bypassing the TCP IP stack within the kernel. The TCP IP stack is still running, so it may be servicing other bits of code, sort of HTTP access or SSL or SSH, sorry, or other types of TCP IP traffic. But the bit where we're writing ST2110 traffic into the NIC to get it into the Ethernet, we use this system called kernel bypass. And that's really difficult to get working. There's a few vendors here achieved that. But I know from having tried it, it's quite a challenge. So this is what we have in terms of a buffer. Now, if you've read the 2110 spec, it talks about the buffer model, where the output rate has a specific number of packets which are written in of frames which are written within a certain time period. So the whole point of the buffer here is to get rid of short-term jitter, which may be occurring within the software. So in the short term, the input rate and the output rate differ. And that's just, it's like the bucket model, where you have just a drip coming out at 10 drips a second, but you're constantly filling up and then leaving and then filling up the bucket. So you have to maintain a certain amount of fullness of the bucket. And that's the analogy we use with buffers. So in the long term, the input and the output rates must be the same. Otherwise, overflow and underflow will occur. But in the short term, we expect the input rates and the output rates to be different. And determining what is meant by short term and long term is a skill broadcast engineers will learn as we continue our IP journey. So this is one of those areas where we have to test and play to try and work out what the optimal sort of short-term buffer and long-term, short-term jitter versus long-term buffer systems are. Because the bigger you make the buffer, the more you increase your latency. And the shorter you make your buffer, the more risk you run of underflow or overflow. So it's a big compromise. Now, one other thing I just wanted to mention, as we've got a couple of minutes, is the unintended consequences. Beware of TCP. If you get the option of removing TCP from your video links, please do. And this is why. TCP is an error correction system. So the idea is you take a load of packets, you send it to your receiver says, yep, I got your 10 packets, sends you an acknowledge, and then you send the next 10 packets. It's like recorded mail, But if you send 10 packets, there's a corruption in the network, and then the other end doesn't acknowledge it, the sending end says, oh, I haven't received an acknowledge, so I'm going to send the 10 packets again, which is all well and good. That's how TCP works. But if your bit rate increases, what you can see is you have to, with TCP protocols such as TCP, you have to differentiate between actual data that is useful that you're transmitting versus all the control data. And you could find yourself with an interesting challenge, such as the red here, where the bit rate increases on the network, but because there are so many losses, you can see the blue line is dropping down, so the actual data throughput significantly decreases. And not only that, because your bit rate has massively increased, you're also stopping all the other services within the system being able to send data. So TCP, large errors can result in many resends, and this gives the impression of a high data rate, but the data throughput is really greatly reduced. And so you've got to be really careful about your analysis tools, because you could put an analysis tool on your network and say, well, it's great, I'm getting 10 megabits a second or 100 megabits a second. The reality is, if you've got a TCP error, 100 megabits, 90 megabits of that 100 megabits a second might just be resends. So you're not actually getting the data throughput you think you're getting. And this is an example I came up with where this could happen. So you could have 3 cameras, for instance. all sending their UDP packets over 2110 through the switch, and then into a vision switcher on the right-hand side. But say, for instance, something went wrong with a TCP. You know, I don't know, maybe there was an error in the code, or there was an error with a NIC or something like that. You could find something like something as low data rate as a desk control protocol, so the bottom one here running at 1 megabits, could tie up the entire network. So you've got to be careful of watching out for those sort of interesting challenges. So, in conclusion, buffers are necessary and a part of IP life. We must have buffers because what we're doing within IP is handing off lots of asynchronous events to each other, and in doing so, we need buffers to synchronize those events. IP networks are bursty by design. We prefer burstiness in IP networks because it makes more efficient use of the data distribution. And understanding the interaction between latency and buffers is essential, and this is something broadcast engineers will come to learn and respect as we continue our IP journey. And we can work with buffers. As long as we know they're there and what they do, we can work with them. And the last point here is, with my sort of editor as the broadcast bridge hat on, I see a lot of PR, I see a lot of press releases coming from vendors. And the latest sort of trend is to say, our box has 0 latency. It doesn't. 0 latency does not exist. I refuse to accept it. I just hit the delete key. And sometimes if I'm nice, I'll just send it back and say, you really should discuss this with your CTO before you send me this rubbish. Information. But 0 latency does not exist. We can get very small latency. We can achieve low latency. And that's the best we could hope for. Thank you.
Great, thank you, Tony. So yeah, I have to really echo your comment about 0 latency. It's a fallacy at best and a complete misunderstanding at worst. But one question I had, just real quick, what do you think is the trend in terms of end-to-end latency with 2110 versus SDI? Is it going to be worse forever? Is it going to get better? Is it, what do you see as being the eventual long-term, settling of that?
I think we have to be realistic about our expectations. I mean, SDI is a fully synchronous network, and so we will always achieve very, very, very low latency from a point-to-point connection. But the disadvantage of SDI networks is they're fixed and unflexible, and they're difficult to change. IP brings us much greater scalability and flexibility. And one of the prices we pay for that is a slight increase in latency. So in the long term, I expect latency to have increased relative to SDI, but I don't know what the exact number is. I don't expect it to be a lot. But I think that's a very, very small price to pay for the flexibility IP is going to give us as we move forward.
Okay, any other questions? Okay, well, thank you very much, Tony.
Thank you.